Hi, welcome to Dark Fact Channel. In this channel, we discuss about historical events. We are happy if you subscribe channel and like posts. You can support us a lot. Well, let's go to this video.
The Chernobyl disaster began on April 26, 1986 with the explosion of the number 4 reactor of the Chernobyl nuclear power plant near the city of Pripyat in the north of the Ukrainian SSR, close to the border with the Belarusian SSR, in the Soviet Union. It is one of only 2 nuclear energy accidents rated at 7, the maximum severity, on the International Nuclear Event Scale, the other being the 2011 Fukushima nuclear accident. The initial emergency response and subsequent mitigation efforts involved more than 500,000 personnel and cost an estimated 18 billion rubles, roughly $68 billion in 2019, adjusted for inflation. It was the worst nuclear disaster in history, and the costliest disaster in human history, costing an estimated $700 billion. The accident occurred during a test of the steam turbine's ability to power the emergency feedwater pumps in the event of a simultaneous loss of external power and coolant pipe rupture. Following an accidental drop in reactor power to near zero, the operators restarted the reactor in preparation for the turbine test with a prohibited control rod configuration. Upon successful completion of the test, the reactor was then shut down for maintenance. Due to a variety of factors, this action resulted in a power surge at the base of the reactor which brought about the rupture of reactor components and the loss of coolant. This process led to steam explosions and a meltdown, which destroyed the containment building. This was followed by a reactor core fire which lasted until May 4, 1986, during which airborne radioactive contaminants were spread throughout the USSR and Europe. In response to the initial accident, a 10-kilometer (6.2 miles) radius exclusion zone was created 36 hours after the accident, from which approximately 49,000 people were evacuated, primarily from Pripyat. The exclusion zone was later increased to a radius of 30 kilometers (19 miles), from which an additional 68,000 people were evacuated. Following the reactor explosion, which killed 2 engineers and severely burned 2 more, an emergency operation to put out the fires and stabilize the surviving reactor began. Following the reactor explosion, which killed 2 engineers and severely burned 2 more, an emergency operation to put out the fires and stabilize the surviving reactor began, during which 237 workers were hospitalized, of whom 134 exhibited symptoms of acute radiation syndrome, ARS. Among those hospitalized, 28 died within the following 3 months. In the following 10 years, 14 more workers, 9 of whom have been hospitalized with ARS, died of various causes mostly unrelated to radiation exposure. It was the only time in the history of commercial nuclear power that radiation-related fatalities occurred. 15 childhood thyroid cancer deaths were attributed to the disaster as of 2011. A United Nations committee found that to date fewer than 100 deaths have resulted from the fallout. Model predictions of the eventual total death toll in the coming decades vary. The most widely cited study conducted by the World Health Organization in 2006 predicted 9,000 cancer-related fatalities in Ukraine, Belarus, and Russia. Following the disaster, Pripyat was abandoned and eventually replaced by the new purpose-built city of Slaviansk. The Chernobyl nuclear power plant sarcophagus was built by December 1986. It reduced the spread of radioactive contamination from the wreckage and protected the site from weathering. The confinement shelter also provided radiological protection for the crews of the undamaged reactors at the site, which were restarted in late 1986 and 1987. However, the containment structure was only intended to last for 30 years, and required sizable reinforcement in the early 2000s. The shelter was largely supplemented in 2017 by the Chernobyl New Safe Confinement, which was constructed around the old sarcophagus structure. The new enclosure aims to enable the removal of the sarcophagus and the reactor debris while containing the radioactive materials inside, with cleanup scheduled for completion by 2065. In power generating operation, most of the heat generated in a nuclear reactor by its fuel rods is derived from nuclear fission, but a significant fraction, over 6%, is derived from the radioactive decay of the accumulated fission products, a process known as decay heat. This decay heat continues for some time after the fission chain reaction has been stopped, such as following a reactor shutdown, either emergency or planned, and continued pump circulation of coolant is essential to prevent core overheating, or in the worst case, core meltdown. RBMK reactors, like those at Chernobyl, use water as a coolant, circulated by electrically driven pumps. 1819, the coolant flow rate is considerable. Reactor number 4 had 1,661 individual fuel channels. each requiring a coolant flow of 28 cubic meters/h, 990 cubic feet/h, at full reactor power, for a total of over 45 million liters per hour, 12 million gallons per hour, for the entire reactor. In case of a total power loss at the station, each of Chernobyl's reactors had 3 backup diesel generators, but they took 60 to 75 seconds to attain full load 2015 and generate the 5.5 megawatt output required to run one main pump. In the interim, special counterweights on each pump would enable them to provide coolant via inertia, thereby bridging the gap to generator startup. However, a potential safety risk existed in the event that a station blackout occurred simultaneously with the rupture of a 600 mm, 24N, coolant pipe, the so-called design basis accident. In this scenario, the emergency core cooling system, ECCS, is needed to pump additional water into the core, replacing coolant lost to evaporation. It had been theorized that the rotational momentum of the reactor's steam turbine could be used to generate the required electrical power to operate the ECCS via the feedwater pumps. The turbine's speed would run down as energy was taken from it, but analysis indicated that there might be sufficient energy to provide electrical power to run the coolant pumps for 45 seconds. This would not quite bridge the gap between an external power failure and the full availability of the emergency generators, but would alleviate the situation. The turbine rundown energy capability still needed to be confirmed experimentally, and previous tests had ended unsuccessfully. An initial test carried out in 1982 indicated that the excitation voltage of the turbine generator was insufficient. It did not maintain the desired magnetic field after the turbine trip. The electrical system was modified, and the test was repeated in 1984 but again proved unsuccessful. In 1985, the test was conducted a third time but also yielded no results due to a problem with the recording equipment. The test procedure was to be run again in 1986 and was scheduled to take place during a controlled power down of reactor number 4. Which was preparatory to a planned maintenance outage. A test procedure had been written, but the authors were not aware of the unusual RBMK 1000 reactor behavior under the planned operating conditions. It was regarded as purely an electrical test of the generator, not a complex unit test, even though it involved critical unit systems. According to the regulations in place at the time, such a test did not require approval by either the Chief Design Authority for the reactor, NIKIET, or the Soviet Nuclear Safety Regulator. The test program called for disabling the emergency core cooling system, a passive/active system of core cooling intended to provide water to the core in a loss of coolant accident, and approval from the Chernobyl site chief engineer had been obtained according to regulations. The test procedure was intended to run as follows. Test preparation. The test would take place prior to a scheduled reactor shutdown. The reactor thermal power was to be reduced to between 700 megawatts and 1000 megawatts to allow for adequate cooling, as the turbine would be spun at operating speed whilst disconnected from the power grid. The steam turbine generator was to be run at normal operating speed. 4 out of 8 main circulating pumps were to be supplied with off-site power, while the other 4 would be powered by the turbine. Electrical test. When the correct conditions were achieved, the steam supplied to the turbine generator would be closed, and the reactor would be shut down. The voltage provided by the coasting turbine would be measured, along with the voltage and revolutions per minute, RPMs, of the 4 main circulating pumps being powered by the turbine. When the emergency generator supplied full electrical power, the turbine generator would be allowed to continue freewheeling down. The test was to be conducted during the day shift of April 25, 1986 as part of a scheduled reactor shutdown. The day shift crew had been instructed in advance on the reactor operating conditions to run the test, and, in addition, a special team of electrical engineers was present to conduct the 1-minute test of the new voltage regulating system once the correct conditions had been reached. As planned, a gradual reduction in the output of the power unit began at 1:06 on 25 April, and the power level had reached 50% of its nominal 3,200 megawatts thermal level by the beginning of the day shift. The day shift performed many unrelated maintenance tasks, and was scheduled to perform the test at 14:15. Preparations for the test were carried out, including the disabling of the emergency core cooling system. Meanwhile, another regional power station unexpectedly went offline. At 1400 hours, the Kiev electrical grid controller requested that the further reduction of Chernobyl's output be postponed, as power was needed to satisfy the peak evening demand, so the test was postponed. Soon, the day shift was replaced by the evening shift. Despite the delay, the emergency core cooling system was left disabled. This system had to be disconnected via a manual isolating slide valve. Soon, the day shift was replaced by the evening shift. Despite the delay, the emergency core cooling system was left disabled. This system had to be disconnected via a manual isolating slide valve. which in practice meant that 2 or 3 people spent the whole shift manually turning sailboat helm-sized valve wheels. The system would have no influence on the events that unfolded next, but allowing the reactor to run for 11 hours outside of the test without emergency protection was indicative of a general lack of safety culture. At 23:04, the Kiev grid controller allowed the reactor shutdown to resume. This delay had some serious consequences. The day shift had long since departed, the evening shift was also preparing to leave, and the night shift would not take over until midnight, well into the job. According to plan, the test should have been finished during the day shift,
and the night shift would only have had to maintain decay heat cooling systems in an otherwise shut down plant. The night shift had very limited time to prepare for and carry out the experiment. Anatoly Dyatlov, Deputy Chief Engineer of the Chernobyl Nuclear Power Plant, CHNPP, was present to supervise and direct the test. He was one of the test's chief authors and he was the highest-ranking individual present. Unit Shift Supervisor Alexander Akimov was in charge of the Unit 4 night shift. And Leonid Toptanov was the Senior Reactor Control Engineer responsible for the reactor's operational regimen, including the movement of the control rods. 25-year-old Toptanov had worked independently as a senior engineer for approximately 3 months. The test plan called for a gradual decrease in reactor power to a thermal level of 700 to 1000 megawatts, and an output of 720 megawatts was reached at 0:05 on the 26th of April. However, due to the reactor's production of a fission byproduct, xenon-135, which is a reaction-inhibiting neutron absorber, power continued to decrease in the absence of further operator action, a process known as reactor poisoning. In steady-state operation, this is avoided because xenon-135 is burned off as quickly as it is created from decaying iodine-135 by the absorption of neutrons from the ongoing chain reaction, becoming highly stable xenon-136. With the reactor power reduced, high quantities of previously produced iodine-135 were decaying into the neutron-absorbing xenon-135 faster than the reduced neutron flux could burn it off. Xenon poisoning in this context made reactor control more difficult, but was a predictable and well-understood phenomenon during such a power reduction. When the reactor power had decreased to approximately 500 megawatts, the reactor power control was switched from LAR, local automatic regulator, to the automatic regulators, in order to manually maintain the required power level. Arkansas 1 then activated, removing all 4 of AR1's control rods automatically, but Arkansas 2 failed to activate due to an imbalance in its ionization chambers. In response, Toptanov reduced power to stabilize the automatic regulator's ionization sensors. Arkansas 1 then activated, removing all 4 of AR1's control rods automatically, but Arkansas 2 failed to activate due to an imbalance in its ionization chambers. In response, Toptanov reduced power to stabilize the automatic regulator's ionization sensors. The result was a sudden power drop to an unintended near-shutdown state, with a power output of 30 megawatts thermal or less. The exact circumstances that caused the power drop are unknown. Most reports attribute the power drop to Toptanov's error, but Dyatlov reported that it was due to a fault in the Arkansas 2 system. The reactor was now producing only 5% of the minimum initial power level prescribed for the test. This low reactivity inhibited the burn-off of xenon-135 within the reactor core and hindered the rise of reactor power. To increase power, control room personnel removed numerous control rods from the reactor. Several minutes elapsed before the reactor was restored to 160 megawatts at 0:39, at which point most control rods were at their upper limits, but the rod configuration was still within its normal operating limit. With operational reactivity margin, ORM, equivalent to having more than 15 rods inserted. Over the next 20 minutes, reactor power would be increased further to 200 megawatts. The operation of the reactor at the low power level, and high poisoning level, was accompanied by unstable core temperatures and coolant flow, and, possibly, by instability of neutron flux. The control room received repeated emergency signals regarding the low levels in one half of the steam-water separator drums, with accompanying drum separator pressure warnings. In response, personnel triggered several rapid influxes of feedwater. Relief valves opened to relieve excess steam into a turbine condenser. When a power level of 200 megawatts was reattained, preparation for the experiment continued, although the power level was much lower than the prescribed 700 megawatts. As part of the test program, 2 additional main circulating, coolant pumps were activated at 1:05. The increased coolant flow lowered the overall core temperature and reduced the existing steam voids in the core. Because water absorbs neutrons better than steam, the neutron flux and reactivity decreased. The operators responded by removing more manual control rods to maintain power. It was around this time that the number of control rods inserted in the reactor fell below the required value of 15. This was not apparent to the operators, because the RBMK did not have any instruments capable of calculating the inserted rod worth in real time. The combined effect of these various actions was an extremely unstable reactor configuration. Nearly all of the 211 control rods had been extracted. And excessively high coolant flow rates meant that the water had less time to cool between trips through the core, therefore entering the reactor very close to the boiling point. Unlike other light water reactor designs, the RBMK design at that time had a positive void coefficient of reactivity at typical fuel burnup levels. This meant that the formation of steam bubbles, voids, from boiling cooling water intensified the nuclear chain reaction owing to voids having lower neutron absorption than water. Unknown to the operators, the void coefficient was not counterbalanced by other reactivity effects in the given operating regime, meaning that any increase in boiling would produce more steam voids which further intensified the chain reaction, leading to a positive feedback loop. Given this characteristic, reactor number 4 was now at risk of a runaway increase in its core power with nothing to restrain it. The reactor was now very sensitive to the regenerative effect of steam voids on reactor power. At 1 hour 23 minutes and 4 seconds, the test began. 4 of the 8 main circulating pumps, MCP, were to be powered by voltage from the coasting turbine, while the remaining 4 pumps received electrical power from the grid as normal. The steam to the turbines was shut off, beginning a rundown of the turbine generator. The diesel generators started and sequentially picked up loads. The generators were to have completely picked up the MCP's power needs by 1 hour 23 minutes and 43 seconds. As the momentum of the turbine generator decreased, so did the power it produced for the pumps. The water flow rate decreased, leading to increased formation of steam voids in the coolant flowing up through the fuel pressure tubes. At 1 hour 23 minutes and 40 seconds, as recorded by the SCALA centralized control system, a SCRAM, emergency shutdown, of the reactor was initiated as the experiment was wrapping up. The SCRAM was started when the Arizona 5 button, also known as the EPS 5 button, of the reactor emergency protection system was pressed. This engaged the drive mechanism on all control rods to fully insert them, including the manual control rods that had been withdrawn earlier. The personnel had already intended to shut down using the Arizona 5 button in preparation for scheduled maintenance, and the SCRAM preceded the sharp increase in power. However, the precise reason why the button was pressed when it was is not certain, as only the deceased Akimov and Toptanov partook in that decision, though the atmosphere in the control room was calm at that moment. According to several eyewitnesses, meanwhile, the RBMK designers claim that the button had to have been pressed only after the reactor already began to self-destruct. When the Arizona 5 button was pressed, the insertion of control rods into the reactor core began. The control rod insertion mechanism moved the rods at 0.4 meters per second, 1.3 feet per second, so that the rods took 18 to 20 seconds to travel the full height of the core, about 7 meters, 23 feet. A bigger problem was the design of the RBMK control rods, each of which had a graphite neutron moderator section attached to its end to boost reactor output by displacing water when the control rod section had been fully withdrawn from the reactor. That is, when a control rod was at maximum extraction, a neutron moderating graphite extension was centered in the core with 1.25 meters, 4.1 feet, columns of water above and below it. Consequently, injecting a control rod downward into the reactor in a SCRAM initially displaced neutron-absorbing water in the lower portion of the reactor with neutron-moderating graphite. Thus, an emergency SCRAM could initially increase the reaction rate in the lower part of the core. This behavior was discovered when the initial insertion of control rods in another RBMK reactor at Ignalina nuclear power plant in 1983 induced a power spike. Procedural countermeasures were not implemented in response to Ignalina, the IAEA investigative report INSAG-7 later stated. Apparently, there was a widespread view that the conditions under which the positive SCRAM effect would be important would never occur. However, they did appear in almost every detail in the course of the actions leading to the Chernobyl accident. A few seconds into the SCRAM, a power spike occurred, and the core overheated, causing some of the fuel rods to fracture. Some have speculated that this also blocked the control rod columns, jamming them at 1/3 insertion. Within 3 seconds the reactor output rose above 530 megawatts. Instruments did not register the subsequent course of events, it was reconstructed through mathematical simulation. Per the simulation, the power spike would have caused an increase in fuel temperature and steam buildup, leading to a rapid increase in steam pressure. This caused the fuel cladding to fail, releasing the fuel elements into the coolant and rupturing the channels in which these elements were located. As the scram continued, the reactor output jumped to around 30,000 megawatts thermal, 10 times its normal operational output, the indicated last reading on the power meter on the control panel. Some estimate the power spike may have gone 10 times higher than that. It was not possible to reconstruct the precise sequence of the processes that led to the destruction of the reactor and the power unit building. But a steam explosion, like the explosion of a steam boiler from excess vapor pressure, appears to have been the next event. There is a general understanding that it was explosive steam pressure from the damaged fuel channels escaping into the reactor's exterior cooling structure that caused the explosion that destroyed the reactor casing, tearing off and blasting the upper plate called the upper biological shield, to which the entire reactor assembly is fastened, through the roof of the reactor building. This is believed to be the first explosion that many heard. This explosion ruptured further fuel channels, as well as severing most of the coolant lines feeding the reactor chamber, and as a result, the remaining coolant flashed to steam and escaped the reactor core. The total water loss combined with a high positive void coefficient further increased the reactor's thermal power. A second, more powerful explosion occurred about 2 or 3 seconds after the first. This explosion dispersed the damaged core and effectively terminated the nuclear chain reaction. This explosion also compromised more of the reactor containment vessel and ejected hot lumps of graphite moderator. The ejected graphite and the demolished channels still in the remains of the reactor vessel caught fire on exposure to air, significantly contributing to the spread of radioactive fallout and the contamination of outlying areas. The explosion is estimated to have had the power equivalent of 225 tons of TNT. According to observers outside Unit 4, burning lumps of material and sparks shot into the air above the reactor. Some of them fell onto the roof of the machine hall and started a fire. About 25% of the red-hot graphite blocks and overheated material from the fuel channels was ejected. Parts of the graphite blocks and fuel channels were out of the reactor building. As a result of the damage to the building, an airflow through the core was established by the core's high temperature. The air ignited the hot graphite and started a graphite fire. After the larger explosion, several employees at the power station went outside to get a clearer view of the extent of the damage. One such survivor, Alexander Yuvchenko, said that once he stepped out and looked up towards the reactor hall, he saw a very beautiful, laser-like beam of blue light caused by the ionized air glow that appeared to be flooding up into infinity. There were initially several hypotheses about the nature of the second explosion. One view was that the second explosion was caused by the combustion of hydrogen, which had been produced either by the overheated steam zirconium reaction or by the reaction of red-hot graphite with steam that produced hydrogen and carbon monoxide. Another hypothesis, by Konstantin Checherev, published in 1998, was that the second explosion was a thermal explosion of the reactor due to the uncontrollable escape of fast neutrons caused by the complete water loss in the reactor core.